So anyway, let me just introduce myself. I'm Benito. I work here at the University of York in the Department of Mathematics. And I'm going to be your host for this session. And so the idea of this little talk is, you know, the theme of this year is place and space. So when I got an email saying this year's York Festival of Ideas topic is place and space, I thought, oh, why not place and space-time, you know? So I thought, okay, I should come and tell people about space-time, which is close to what I do in my research. And so that's what I'm planning to do today. So the title is A Cosmic Odyssey, Our Place in Space-Time, okay? So if anybody is here because of the Christopher Nolan film, which is coming out, you're in the wrong place. However, it'll be nevertheless fun, so please stay. All right, let's get started. So let's start with something, let's say, very deep in some sense. Okay? So for some reason, humans, we've kind of always asked ourselves what our place is in the universe, where we are, why are we here? What does it mean, right? And there have been a number of answers in the few years that we have had civilization. Probably there were some answers before we had writing systems, but we have no access to those answers. But anyway, for the most part, many cultures, many ancient cultures, and even all the way to the Middle Ages, we used to think that we are the center of the universe. It's a quite natural idea, if you think about it. Very clever people thought we are the center of the universe. I'll give you an example of one very clever person and the argument that they used. Aristotle, do you know who he is? Yes, very good. Everybody knows him. So a very clever philosopher, Greek philosopher, and he said, heavy things tend to go to the heavy center, and if I drop things, they fall to the earth. Our feet are on the earth. When we jump, we fall to the earth, and we see all those stars revolving around us. The sun, the moon, we see other planets in the sky. Clearly, we are at the center. This was Aristotle's idea. It's a clever idea. It's a clever argument. However, it's wrong. Okay? Even back then, some people thought that we were not at the center of the universe, but they didn't really have a solid mathematical theory for it. It's rather that there were many ideas out there, and some of those ideas, well, said, no, we're not at the center. Some others said, we are. Anyway, people that thought that the Earth is at the center of the universe were very good at drawing pictures, and they could draw beautiful diagrams like this, which are, however, wrong. And then people that spent their time thinking maybe a little bit more carefully, they were not so good at drawing pictures, but they could draw correct diagrams. So the diagram that you see on the right is coming from Copernicus' book, De Revolutionibus Orbium Celestium. Okay, so it's about celestial revolutions, right, and orbits. And you can see in this diagram, the sun is placed in the middle, and then you have the planets as we learn them more or less. Okay, as we learn them more or less when we are at school, right? You have a solar system with the sun in the middle. Now, what was the idea? Why was Copernicus thinking about this, that we are not in the middle? Well, it turns out that by the time that Copernicus was around, we actually had a lot of observations of the sky. And we had more or less an idea of how planets were moving in our, let's say, our celestial on the sky, right? And people devised very clever ways to put the Earth in the middle and then do some calculations of how the planets moved and give them some regularity. But the calculations were kind of complicated. Copernicus realized that if you put the sun in the middle and you put the planets going around, the calculations get easier. However, his calculations were not perfect because he thought that everything was revolving around the sun in circles. And it's actually not quite correct. So, as you might know, we go around the sun following ellipses. So this is very natural idea today, but it wasn't so obvious back then. Circles are nice, they are perfect. The universe is perfect, there should be circles, no? However, it turns out they're not, and for good reason. So the first person that pinpointed this precisely into a set of physical laws was Kepler. So Kepler didn't have a theory of the motion of planets, but he also didn't have Instagram. And this allowed him to look at astronomical tables with a lot of data and focus intensely, right, to try to get some regularity out of all these numbers. So out of this information, he came out with 3 laws, which are called the Kepler's laws of planetary motion. So the first law is that planets revolve around the sun following an elliptical trajectory, and the sun is placed at one of the foci of the ellipse. So each ellipse has 2 foci, and the sun is sitting exactly at one of them, and the planets follow the ellipse. So that's the first law. The second law said that if you draw lines between the sun and the location of the planet, and you do that sometime later, after the planet has elapsed some time, you can draw a little area spanned by this kind of triangular shape there. And Kepler realized that they span equal areas in equal amount of time. Okay? That's the second law. And his third law was that it was about how long it takes for planets to revolve around the sun. And he observed that the square of the time that it took for a planet to go around was proportional to the cube of the average distance between the planet and the sun. So very far away planets take disproportionately long time to go around the sun compared with planets that are very close to the sun, which do it very quickly. But he gave these exact, ratios with cubes and squares. So very, very mathematically precise. However, no real mathematical theory of why the planets move this way. Now, there was another gentleman that was very clever. He also didn't have Instagram, so he could focus for a huge amount of time. And there was also, there was also the fact that he had to go home. He was studying in Cambridge, and then there was, I think, the pest or something. He had to go home. He was bored, and he decided to study on his own and come up with a beautiful book called De Philosophiae Naturalis Principia Mathematica. This gentleman is Isaac Newton. Isaac Newton came up with the laws of mechanical motion that we now call classical mechanics today. And he described essentially how bodies move and interact via forces in the form of 3 laws, which are called the 3 laws of Newton. But in particular, for our purposes, what is important is that he was also able to derive what Kepler had observed. Okay? The way he derived Kepler's laws was, of course, using his Newton's laws, but also inventing something that we call the laws of gravity, the Newtonian laws of gravity. So he basically came up with an equation that explained how planets orbit around the sun, and he was able to calculate all the things that Kepler had observed and noted in his 3 laws. So in particular, he was able to derive that indeed planets follow ellipses. The second law about these areas spanned by the motion of the planets, he was able to understand that this was a consequence of his law of gravity together with the conservation of angular momentum, which is also an important feature when we ride bikes. Just fun fact. And And then, of course, the third law also came out of his law of universal law of gravitation. So everything was amazing. There were some people that were not so happy with some philosophical aspects of his equations. One aspect that was not very satisfactory was that it relied on something called action at a distance. In other words, Newton was able to derive the Kepler's laws by having the sun and the, let's say, the Earth, if this were the Earth, exerting a force onto each other. However, it was not like all the other forces, right? It was not like, I push something with my hand and I make it fall. The sun is very, very far from the Earth, and so it was a strange force. It was called an action at a distance, and it was acting instantaneously. So it was a bit strange. Some people pointed this out, but, it was very good mathematics. It gave you the right answers. So people, went on with it, and it's an incredibly successful theory of gravity. Sometime later, people started studying other phenomena, in particular, electromagnetic phenomena. And electromagnetic phenomena had similar equations to the laws of gravity, but they were a little bit different. In particular, one could also, as maybe informally, if you have charges of opposite sign, they attract each other. If you have charges of the same sign, they repel each other. But they don't do it with action at a distance. All this repulsiveness and attraction is mediated via something called the electromagnetic field, which was then devised around that time in the 1800s when people were studying electromagnetic phenomena. One of the people that was studying electromagnetic phenomena was a Scotsman called James Clerk Maxwell, and he understood that the electromagnetic field in the absence of charges was also an interesting thing to study. And when he started studying this, he realized that one could find a solution to certain electromagnetic equations, which we now call Maxwell's equations. And he could find a solution in which the electromagnetic field propagated as a wave. And it propagated at a certain speed, and that's the speed of light. And so Maxwell, in studying electromagnetic phenomena, understood that light travels at a certain speed, and that such a speed does not depend on the state of motion when we observe light. So this is very counterintuitive. Think of a car receding from you at 50 kilometers per hour, or 50 miles per hour if you're more comfortable with that. You see it receding, receding, receding. However, if you're going at 40 miles per hour and it's receding at 50 miles per hour, then effectively it's only moving at 10 miles per hour with respect to you, right? You don't see it recede so fast, but you're it's just receding at 10 miles per hour, okay? Light doesn't work like that. If you go at half the speed of light, chasing a light ray, it still recedes from you at the speed of light, okay? So it doesn't obey, light doesn't obey the intuitive laws of motion that were well understood since the Newtonian times and even before. Okay? Now Einstein, who is another clever man from the late 19th and 20th century, Einstein wasn't having it. He said, well, the electromagnetic theory that we really like is inconsistent with the mechanical laws of Newton that we also really like. Something has to give. And he started playing around with these ideas, and he understood that rather than declaring that these electromagnetic laws were wrong, there was something fishy with Newton's ideas. So he devised a new theory that we now call special relativity, which accounted for the fact that the speed of light is always constant for every observer. Okay? The way in which he did it is by giving up on an important notion that was subjacent in Newton's work, which was that time and space were absolute in Newton's description of the universe. And Einstein said, well, maybe time and space should not be absolute. But the speed of light should be absolute. Okay, this is quite a big analytic jump, I think. However, he turned out to be correct. And there are many, many beautiful ways of thinking about this, but here's one, okay? So suppose that you are standing somewhere at rest, and then two lightnings strike at equal distance from you at the same time. Boom. So you hear the thunder, and then the light comes to your eyes, and you see that they landed simultaneously, okay? Now, if you repeat this experiment as you are moving, remember the speed of light is constant. Let's say you're moving in this direction, and you pass exactly through the middle, where I was sitting, and then the two lightnings strike. Now, what happens is you're moving in this direction, so the light coming from this lightning will come to you first, and the light coming from that other lightning will take a little bit longer. So from your perspective, this is not a simultaneous event. There's one lightning that happens first and another lightning that happens later. Who is right? Did they happen at the same time or not? Now, this is an example of how the notion of time and simultaneity is different for two different observers. And I draw here the equations of the transformation laws of special relativity just for the fun of it. You can see that they are very simple, okay? So let's move forward. This was 1905. Einstein was very happy, I suppose. He had come up with these new laws of mechanics, of special relativity, that were consistent with the equations of electrodynamics, and that also were small corrections to the Newtonian way of understanding the universe, so that in ordinary situations they would give you more or less the same result. They would give you effectively the same result for every practical purposes. So still for, two cars chasing each other, they would give you the right answer, because the factor of correction was very, very tiny, that you could only detect it when you moved at speeds that are near the speed of light. Okay? So he was very happy with that. On the other hand, he wasn't very happy with gravity. Okay? So Newton's laws of gravity relied on Newton's mechanical understanding of the universe. They were built upon the foundation of a fixed notion of space and time that is absolute, and they were not, based on this new foundation that time and space are relative to an observer. Okay? Now, at this point, the struggle begins. Okay? Einstein spent more or less 10 years of his life working intensely, trying to come up with a theory of gravitation that was consistent with his theory of special relativity. Okay? And it was a long struggle. The first important ingredient was the ingredient of space-time. Now, when Einstein formulated his special relativity theory, other mathematicians of the time, such as Minkowski or Poincaré, they were very, very close to getting to a similar understanding of the laws of electromagnetism, the symmetries of electromagnetism, and they were very, very close to understanding special relativity. In particular, Minkowski understood that there was a very, very natural way of framing Einstein's special relativity in terms of something called space-time. Okay? So you could think of all dynamical situations happening not in space with an absolute time, like Newton had thought about the universe before, but in a certain space-time. Okay? And space-time was, you should think about it as a four-dimensional space, roughly speaking, in which time is a special direction. Okay? So what is this 4-dimensional space with 3 lengths and 1 time direction? Well, it's our usual 3D, 3D space with up, down, forwards, backward, and then sideways, left, right. But in addition, with another time coordinate, which doesn't behave exactly like the spatial coordinates. In particular, you may have noticed that you can only go forward in time in your daily experience, right? We can't really go backwards. So that's a feature of this asymmetry of time in space-time. Okay? And in particular, one could think of space-time as a flat 3-dimensional mesh of space and a time running in the let's say in the upwards direction, imagining at a fixed rate, so also flat in the time direction. Okay. So how does one then get to incorporate gravity into special relativity? Is by taking very, very seriously this idea of Minkowski of space-time. Is to not think about there being space and time, but think of it as a unified entity called space-time. Okay? So, let's think together with Einstein and let's derive the laws of general relativity in this room. Okay, we will not derive all the mathematics, but we will get the main idea together. Okay? Okay, so this is what happens. Special relativity says light is very important. It always travels at constant speed. Now let's think about gravity. Einstein was thinking that the essential feature of gravity is that you can sort of trade it for acceleration. So think about the following. If you jump off a building, right, at first your velocity is not very high, but then it gets higher and higher and higher because you accelerate as you fall down, and then of course the dramatic end of this fall, you have accelerated quite a bit and your velocity is quite high. Okay, so gravity, you could think of it in terms of acceleration. So in particular, the acceleration produced by the gravitational potential of the Earth in Newtonian mechanics is something like 9.81 meters per second squared, if you've studied this at school at some point. So that's an acceleration rate which is determined by the Earth's gravitational potential in our case. Okay? So Einstein was thinking about gravity in terms of acceleration, and he was imagining the following experiment. Suppose that I am in a room with no windows on planet Earth, okay? Now, what can I deduce from this? What I can deduce is that the Earth is below my feet, and I'm just standing on the floor, and I feel this gravitational attraction towards the floor. If I drop an object, it will fall and fall on the floor. Okay. The rate of acceleration again is 9.81 meters per second squared. Okay. Now he was thinking the following. Well, the room that I just described has no windows. I cannot really see what is outside. Now imagine the following situation. I'm not on planet Earth, but instead I'm in space. Okay? I am out in space where there is no gravity, essentially. You're floating about freely, but you're inside a rocket. Okay? And the rocket is accelerating in a certain direction at 9.81 meters per second squared. Now what is going to happen to you as the rocket accelerates? Any ideas? Well, you're going to kind of fall down, right? So if it accelerates in this direction, I'm going to fall into the wall that is opposite, right? To the, and I would say, so, it's like falling on the floor, right? Since you imagine in this experiment that there are no windows and you cannot see the stars outside or you cannot see the trees when you're on Earth, or the space when you're in outer space, you actually cannot tell the difference between being in that rocket or in that spaceship accelerating, or being on Earth without moving through space, right? Okay, I say the without because of course Earth moves through space, but that's not the point. So in this way of thinking, acceleration and gravity are completely indistinguishable. You would not be able to tell if you're in the rocket or if you're on Earth. Is this point clear for everyone? Yes, okay, excellent. Now Einstein, who was very, very keen to think of the consequences of special relativity and the speed of light being constant and so on, said, well, imagine I'm inside the rocket and I hold a torch, or maybe a laser beam, but there were no laser pointers when Einstein was thinking about this. But suppose I hold a torch and I shine, I send a ray of light at the height of 1 meter, holding it straight parallel to the floor of the rocket as the rocket accelerates. I shine the light like that, straight. Now what's going to happen to that light ray? Is it going to reach the opposite wall at the height of 1 meter? Or is it going to reach the opposite wall a little bit lower than 1 meter, in your opinion? Remember that the rocket is kind of moving upwards, right? So since the rocket is moving upwards, as I shine the light, by the time that it reaches the other end of the other wall inside the rocket has already moved upwards a little bit, and it will not land at the height of 1 meter, but it will land a little bit lower, right? So the light in outer space was moving along a straight line at roughly 300,000 kilometers per second, which is the speed of light, to reach the other wall. But in that time, the rocket moved upwards, so it doesn't land exactly at the height of 1 meter, but it's a little bit lower because the rocket, of course, this is like super subtle, right? Because the rocket is moving, not at speeds comparable to the speed of light, but this is why Einstein was thinking about it and not actually performing an experiment, right? So is this point clear? Okay, so that's the rocket story. But of course, as I said, the room is dark, there are no windows, you don't know if you're in the rocket or if you're in the rocket or if you're on Earth. So if you did the same experiment on Earth and you shone light, now what's going to happen? Is it going to go straight or is it going to bend a little bit down? Now you have two choices. Either we devised a way of distinguishing the rocket from the Earth, or if we are Einsteinian, we conclude that the light bent down a little bit because of the gravitational acceleration, because of the gravitational potential. Okay? So instead of the rocket landing a little bit lower because instead of the light beam landing a little bit lower because the rocket moved upwards, it lands a little bit lower because the Earth pulled the light ray with its gravitational potential. Okay? And this led, so by the way, Einstein was fascinated by this. In his biographies, if you have read about him, he says that this was the most beautiful thought in his life. This experiment, it wasn't, when his son was born or when he got married. It was this thing with rockets and the Earth and gravitational field. Okay, fine, great man, nevertheless. So of course, in context, he probably meant this is the most beautiful thought in my professional life, but whatever. Okay, so he thinks light bends down a little bit because of the gravitational pull of the Earth, right? It's a very interesting thought. Like nobody had thought of in these terms before. Okay? So he still doesn't have a law of gravity, Okay, he still doesn't have equations of gravity, but he's back to the Keplerian situation where he can observe some phenomenon without precisely explaining it mathematically. So around 1911, so let's say 5-6 years after special relativity, this was already clear to Einstein. And he had already told some astronomers that gravity should cause light bending. And fortunately, so at first he came up with some predictions that were wrong because he still didn't have the right theory. And hopefully astronomers were not able to measure light bending at that point because he would have been wrong by the number that he gave. But he kept trying to get some equations for gravity, and he was talking to some people who were geometers, such as Levi-Civita, Tullio Levi-Civita, also David Hilbert, who knew a lot of geometry and a lot of mathematics in general, Marcel Grossmann, who had studied with him when he was a student in Switzerland, etc. And it eventually became clear that geometry was the right idea to capture these things, okay? So to capture how a light ray would not follow a straight path but would bend around, the right idea was to think that space-time described a certain geometry, and the reason light rays bent around in gravity is because space-time got deformed, okay? Space-time got deformed. So this is the same idea if you draw a straight line on a ball, it doesn't look straight, it looks curved, okay? If you draw a straight line on a curved surface, you cannot draw a straight line. You draw a line that more or less follows the surface, right? So this is the idea. The light rays bend because of space-time curvature. And it took him a long time, but in 1915, he came up with the right equations of general relativity. And this equation said that matter and energy are the source of space-time curvature. The effect that that curvature has is precisely that things don't go on straight lines. So if you're a planet around the sun, the space-time curvature produced by the sun makes the planet follow an ellipse, okay? And if you're in outer space where the gravitational field is effectively zero, negligible, curvature is negligible, then you go on a straight line, okay? So space-time curvature and gravity are the same phenomenon, okay? Now, this is the only diagram that I drew myself. All the other ones are, done by other people. But I like to think that it captures the right idea. So let me explain. This is what Arthur Eddington was hunting in 1919 in a solar eclipse that was observable from Príncipe in West Africa and Brazil in South America. So two teams went to see the solar eclipse, not just because solar eclipses are cool, but also because they wanted to observe a prediction of Einstein's relativity. So what Einstein was saying is, so astronomers, Arthur Eddington was a very, very prominent astronomer. So astronomers knew more or less where stars were going to be located when this eclipse took place. And because in a solar eclipse the sky gets dark, you can actually see the stars with the right telescope, okay? And what Einstein had pointed out is that if there is the presence of a very massive body and a light ray is traveling close to it, it gets deflected. And then it goes into your instrument, such as a telescope, at the wrong angle, okay? The wrong angle, okay, at the real angle, but okay, it's not a straight line, all right? So from your perspective, you would trace it back to a different location. You would say that the star was here instead of being down there. And they were looking for this phenomenon in this eclipse, okay? They were looking for that little angle deficit that would confirm that light bends because of the gravitational field of the sun, okay? And because space-time is curved around the sun. And indeed, they made this observation. There is, like in more modern biographical notes, there is a lot of questioning as to how good their observations were, because apparently it was cloudy and whatnot. But maybe they had a window where they could see the phenomenon and then write down in their notebooks, etc. And they found exactly the prediction of Einstein, exactly the right angle of deflection for the star that they were looking for. And Arthur Eddington was just thrilled. This is the time of the war, right? This is like First World War type thing. Germans are not nice people. The English don't like the Germans. Arthur Eddington he was the evangelist for Einstein in the UK, okay? He was his biggest defender in Britain. And he gave this, he wrote this little poem at the dinner of the Royal Astronomical Society, which is kind of a play of words on an old Iranian or Persian poem. And it says, oh, leave the wise our measures to collate. Well, okay, they can measure things and write them down, whatever. One thing at least is certain, light has weight, okay? One thing is certain, and the rest debate, light rays when near the sun do not go straight, okay? So he was, a charming lad. Okay, probably, he had a few drinks and whatnot. But yeah, this was just after this, the popularity of Einstein exploded. That's when he becomes the Einstein that we all know, superstar, celebrity, reported in the New York Times, etc., and whatnot. Okay, so where are we today with Einstein's theory of gravity? So remember, this is the Cosmic Odyssey, our place in space-time. We have just a few minutes left before we start questions. Let me tell you a couple of things that we are trying to understand today about gravity and the universe. On the top we have the result of a 5-year survey by an American telescope called DESI, which has mapped close to 50 million galaxies in the universe. And what it is looking for is trying to understand the expansion of the universe. So we know, thanks to Einstein's theory of gravity and observations of very powerful telescopes, that our universe is in expansion, okay? So every star is receding from every other, star, roughly speaking, okay? Or every galaxy is a more large-scale phenomenon. So let's say all galaxies recede from each other, and if you are Einsteinian, you just don't say that galaxies are moving, but you say that space-time is expanding, and that's why every galaxy is receding from each other. Much the same as when you blow a balloon, it enlarges, and if you draw a few dots, the more you blow the balloon, the less apart the dots are. This is exactly what's happening in our universe, and we understand more or less why the universe is expanding. There are some debates. The Einstein equations can account for this expansion, but there is still a little bit of doubt left among cosmologists if the explanation is complete. Anyway, I'm just showing you this picture for two reasons, okay? The first one is that the first picture that I showed you was very, very beautiful, but was wrong. And this one is right, and it's also very beautiful. I mean, it's incredible. If you imagine each one of these dots is a galaxy, and we are looking up to 7 light years in the past to the galaxies that are furthest away. I think this is just humbling. It's amazing. And it's just, if you think about it, I don't think you can process it. I cannot process it. I mean, the universe is huge, and this is just what we can see. There are things that we cannot even see, that we haven't mapped, that are too far, and it's just incredible. You have seen that there are 2 wedges. What are those?
just stuff we haven't mapped yet.
It's true, but also I'll tell you why we haven't mapped. Because if we look in the direction of the Milky Way, we cannot map. Basically, there's too much light, we cannot see far away. There's the Milky Way, all those stars shining in our face. There's no way to have a clear sky. So what we see here is the planes that are orthogonal to the Milky Way. Okay, so we see up, we see down, whatever up and down is in this context, and Milky Way is here. The second reason is that, okay, we are the center of the universe in some sense, but that's up to you. That's up to you to define, right? There is no center of the universe. Every point can be the center of the universe in a suitable and appropriate system of coordinates. We have our system of coordinates here on Earth. We are the center of the universe. Not in that old philosophical sense, but you know what I'm saying. We can observe from here. We can look far. We're happy. The other huge prediction of general relativity, actually the first solution ever found, is called a black hole. It was first observed by the Event Horizon Telescope collaboration not long ago, just a few years ago. And this is a black hole that is in the center of a galaxy called Messier 87. It's been christened as the M87 star black hole. And this is how it looks on the telescope, right? Bright here, less bright up there, and then black in the middle. So what you're seeing in the middle is what you're not seeing, actually. That's the black hole itself, okay? There's no light emanating from it. Black holes swallow light because their gravitational field is very intense. Now, from very close by, of course, with our telescopes, we can't really get that resolution. But with mathematics, we know how they look, right? So again, here, what you don't see in the middle is the black hole. And what you see here is a ring of light and matter going around the black hole and eventually escaping to our telescopes, or to our, if we are sitting here, coming to our eyes. This thin, bright bit here is the light that is escaping to us, that can escape, that is closest to the black hole itself without falling back into it. I will not explain exactly in all detail, but the black hole actually doesn't start there. It starts a little bit further in, okay? But what happens is that the light that gets sufficiently close to the black hole, it eventually falls in. So we can just see light that is a little bit further out from it, okay? And then there is this crown, which is strange, right? What do you think this is, this crown that we see? So I'll tell you. The black hole is rotating, so there's a lot of light, plasma, matter going around it at very, very high speeds, close to the speed of light. And the light going at the speed of light, of course. And it's going around. The black hole is distorting all the space-time around it. It's very, very intense gravitational field. So what you see up here is the back of that ring. Okay? How is it that you see the back of that ring? Well, imagine there's the back of the ring. There is some light coming off like that. It should normally shoot up, but the black hole is like, come here, come here, come here. And so it whoop, bends and reaches our eyes. Downstairs, same phenomenon with light coming from the bottom. So this is the back of the ring. This is the front of the ring. The brighter side is coming in our direction. It looks brighter due to an effect called gravitational blue shift. And the dimmer side is going towards the back. Okay, so that's more or less how you read this nice picture. If you've seen, if you like films, you've seen this in a film. I forget the name, but anyway. Anyway, where the magic happens, where you can study all these nice phenomena that I just talked about, is the Department of Mathematics of this university. Big commercial. It's just right there. Look out the window. That's the Department of Mathematics. That's where the mathematical physics group works. That's where I work. I'm a member of that group. And this is a picture of a blackboard inside that building. This is my handwriting, not so nice. This is a diagram of an evaporating black hole as drawn by a mathematician. Okay, this is a black hole evaporating due to quantum effects. In our group, we know how to read this diagram, and that you can do if you study in York with us. Okay, thank you very much. So we have maybe 15 minutes for questions if you yeah? Yes.
Right. Well, you know you get black holes. You also get white holes as well.
Yes. So I can
Explain that.
yeah, I can tell you all about white holes. So the first, as I mentioned this very quickly, but let me now say it in more detail. The very first mathematical solution that was found to Einstein's equation of gravity, called Einstein's field equations. Einstein field equations are super hard to solve, okay? They are super, super hard to solve. They are what we call a nonlinear system of partial differential equations. So the geometry is beautiful, huh? But when you try to solve the monster, it's a beast, okay? So it's what we call a system of partial differential equations that is nonlinear, and it furthermore has something called gauge. It's a mess, okay? However, in 1915, when the equations of general relativity first came out, there was a Prussian gentleman called Karl Schwarzschild that got a hold of a copy of Einstein's article while he was in the trenches, and he tried to solve them. And he tried to solve them in the easiest way. He said, let's try to get a solution of a perfectly symmetric object of perfect spherical symmetry, and let's have a solution that it's static. It means it doesn't change with time. So you're just looking for a solution that has the symmetry of a sphere and it doesn't change with time. Okay, so it could be like a sphere that doesn't rotate or something like that. So he's trying to get a solution. He's not trying to model something physically. Okay, and he finds a solution which we now call the Schwarzschild black hole after Karl Schwarzschild. Unfortunately, I think Schwarzschild didn't live to see his fame because he was probably shot by one of your ancestors in the trenches or something like that. But yeah, anyway, his solution became probably the very first exact solution that is studied in a course of general relativity. Okay. Now, Schwarzschild at that point did not understand the solution completely, but today we understand it a little bit better. And what he found was what we call a static black hole. Okay, it was the first black hole that was found, and it's a black hole that doesn't rotate, so it's not like the one I showed you, but it's just sitting there not doing anything. Now, that black hole has what we call an analytic extension. It means that what you have found in the solutions mathematically is actually not the most complete solution, but actually the most complete solution of that space-time has a mirror in the past. Okay, so it has a black hole region, and in the past of the black hole, it has what we call a white hole region. Okay. Okay. So what is a white hole? So a black hole is a thing that is very, very heavy, and it eats everything. It eats so much intensely that it swallows light, and this is why it's black, because it doesn't reflect any light, right? So this is why it looks black. Now, a white hole is its anorexic twin. Instead of eating everything, it spits out everything, okay? So nothing can stay inside a white hole region. Everything must come out. I said anorexic, but I meant bulimic. So it vomits everything out instead of swallowing in. Are there white holes really in our universe? That we know there are no white holes in a universe. So when I said these white holes are solutions, they are analytic extensions of the Schwarzschild solution, but nevertheless such an analytical extension doesn't come out of solving the Einstein equations as a dynamical system. They come out of some mathematical argument. Okay. Also, Schwarzschild black holes, we don't think they exist in nature because there aren't really any things that are perfectly static, not moving, etc. We think that black holes must have rotation. Okay. Those are called Kerr black holes. But no, white holes are what we call theoretical solutions of the Einstein equations, but they are not, as far as we know, physical solutions of the Einstein equations. So the idea of the Einstein equations, Einstein field equations, is that you have a set of equations, you can solve them, you can obtain solutions. It doesn't mean that the solution that you obtain corresponds to a physical situation. For the solution that you obtain to correspond to a physical situation, you need a physical model of a situation. You need to say, I have this amount of dust, I have a planet here, I have a star over there, the universe is expanding like this. So this is a physical solution. You are giving it some input. The equations are just a machine. You give them something, they spit something out. But you need to give them something physical. If you give them something unphysical, they spit something unphysical out. Okay? So that's...
So rotational black hole,
Yeah.
a white hole.
So rotational black holes, they are a little bit more complicated if you play this trick. They don't just have a black hole and a white hole like in the static case, but they actually start copying each other. You have an infinite tower of copies of the solution extending to the past and to the future. And in that case, what you have instead is that you can tunnel into different... This is getting crazier and crazier, but you need to kind of get it with a pinch of salt again. I will explain. This is again unphysical, but what you get is that you can tunnel into different universes by going inside the black hole and then exiting in the next, let's say, white hole exit, if you will. But again, this tower of solutions that are just copies of each other with different universes copied. These are, again, solutions that we obtain by this analytic extension that I was saying. And so they are mathematical solutions to the Einstein equations, but they are not physical solutions that correspond to real situations in our universe. They are furthermore probably, in the case of this rotating black hole, they are probably unstable solutions. What that means is that they cannot be produced by a physical process, but they are just, let's say, mathematical. So let me give you an example. In Newtonian theory, you can solve Newton's equations and make a feather stand on a table. You can do that, right? You can perfectly balance the feather, no wind, the feather stands there. Now, in real life, I dare you to do that. It cannot really be done. You cannot, by a physical process, do that. Now, these solutions are a bit like that, okay? They are not produced by physical processes. Yeah.
I think I did in Doctor Who, I think.
Ah, right, okay, yes, excellent. Yes, question over here, then over there, then over there. First you?
So you mentioned analytic extensions. I hope that I got that right.
Yes.
In that some solutions can have mirrors, and I was wondering why this idea of symmetry is like such a big thing in like quantum field theory and all that not mumbo jumbo, but like
Yes, mumbo jumbo. Yes.
Sorry, I can think of another word.
Yes. So why symmetry is important?
Yeah, why symmetry is why we need to have like symmetric particles in the standard model and all of that.
Okay, so symmetry in the context of physical theories and physical models is very important because it serves as a guideline of the physical content of a theory. So we know that we can organize theories by their symmetry. Historically, the first example is Maxwell's equations. Maxwell's equations have a special type of symmetry, which is called Lorentz symmetry, and is the type of symmetry that is not in Newton's equations, but is there in special relativity. Okay? So symmetry is about how you repackaged a set of equations into a different system that is equivalent. Okay? So this is the idea of symmetry. And the symmetry of general relativity is a very, very large symmetry. It's a symmetry under change of coordinates. It means you can describe space-time with whatever coordinate system you want, and you're describing the same system. But the symmetries in the standard model that you were mentioning are some type of symmetry that is called internal. They are not about rearranging coordinates. They are about symmetries in the way that you organize the field content of the theory. This is the type of symmetry that also Maxwell Maxwell's equation has, but it's not this Lorentz symmetry that I mentioned. In the case of Maxwell, it's something called U1, whatever, doesn't matter. But other theories in the standard model also have symmetries. And for example, a symmetry might tell you that some interaction is forbidden while another interaction is allowed because it has the same symmetry as the rest of your theory. Yeah. Okay. Sorry, overly too technical.
No.
There was another here, and then you.
Just a question about the principle of equivalence. So you mentioned that, earlier in the talk, that gravity is equivalent to some accelerating Riemanns in space. So gravity is obviously associated with the curvature of space-time. So in that case, does it mean the accelerating room, or accelerating elevator, is inducing some sort of curvature in the space-time within it as well? Because earlier you said gravity grabbed the light. Well, obviously, if it's massless, then how would it be attracted due to gravity? Then if it's not the grabbing, then is it the curvature in space-time? Would it make sense to describe it that way or not?
So the whole point of the accelerating rocket or lift, as you want to think about it, this equivalence between acceleration and gravity is it's in a sense relativistic, but in a sense it's not, okay? This is like a little bit pre-full general relativity reasoning, okay? This is when you have special relativity, you have Newton's theory, you try to see what you can extract out of it. Now, in the full general relativity way of understanding things, we say that the light that is moving along a curved trajectory is not accelerated. So the dogma gets reversed. Now you say things that move only under the influence of gravity, that is, that they follow the straightest possible lines, the curves in space-time, you call those not accelerated. You call those geodesics. And what you call accelerated is something upon which an external type of force is acting. So, for example, if you have an electromagnetic field, it might have an effect on charged particles, and then those charged particles will not just follow the motion of gravity. But if you have a neutral particle and the electromagnetic field does nothing to it, then that will move in an unaccelerated trajectory, although that unaccelerated trajectory looks not like a straight line. So in the Einstein way of thinking, in the general relativity way of thinking, when you fall off a building and you land on the floor and you break, let's say, your shoulder, what breaks your shoulder is not gravity. You were moving freely. You were moving freely doing what gravity tells you to do. What broke your shoulder is the force that the floor exerted on your shoulder, and that's why it didn't break as you were falling. It broke when you fell and hit the floor. So going back to the rocket or elevator, there is a force that is being applied in the rocket case, which is the force of the motors that are pushing the rocket. So the situation is not exactly equivalent in that case. Yeah. But that's, yes.
Yeah, I'm reading, they keep kind of imitating or recreating the effects of black holes at CERN in Switzerland, and reportedly, as such that they can even apparently open doorways to other dimensions. And I was just checking, the mathematics is all there, and I just want to double check if they won't develop a black hole that will generate more force than they intended. I'm sure they really know what they're doing. They really know the results. Yeah.
Okay, so as far as I know, people are not trying to engineer any real black holes. There are some type of experiments that are called analog gravity experiments, in which people study systems that look like black holes, so arrangement of lasers, etc., that give an effective region where they trap something. They trap light or whatever. But they are not black holes in the gravitational sense. I think those experiments are not being done at CERN, but they are being done elsewhere. They're called analog gravity experiments, and they use them to kind of test ideas of general relativity in simple tabletop experiments. So they don't really have any black hole features in the gravitational sense, but there are some analogous features there. Now, what would happen if somebody tried to engineer a very, very small black hole in some complicated way, we think, is that it would evaporate very quickly due to quantum effects. So you couldn't really use it to jump in or anything like that. Black holes are more stable when they are very big, when they are very small, if we understand, and we don't understand everything correctly, but if we understand what we understand correctly, is that they would evaporate rather quickly. Yeah. Let me see how we're doing with time. If we have time for more questions, you too. Let me just moderate myself with how much fun we can have. Unfortunately, we run out of time. It's 4, and I guess, yeah, we can chat outside if you're happy. And yeah. Okay, thank you very much.